When dealing with large number of trials in a binomial situation, making direct calculations of the probabilities becomes tedious or outright impossible. Fortunately, the normal model comes to the rescue. As long as the success-failure condition holds, we can use normal model to approximate binomial probabilities. The success-failure condition is a binomial model is approximately normal if we expect at least 10 successes and 10 failures. In other words, if we can get NP is greater than or equal to 10 and NQ greater than or equal to 10, we can use a normal approximation. When we use the normal model to approximate the binomial model, we are using a continuous random variable to approximate a discrete random variable. So when we use normal model, we no longer calculate the probability that the random variable equals a particular value, but only that it lies between two values. An airline, believing that 6% of passengers fail to show up for flights, overbooks. Suppose a plane will hold 320 passengers and the airline sells 335 seats. What's the probability the airline will not have enough seats and will have to bump someone? So what we need to do is find the mean and standard deviation. So to find the mean, we're going to take n times p. N is 335. P, our probability of success, is 0.94. The reason we use 0.94 is that we have 94% of the people that are going to show up. So that is equal to 314.9. Standard deviation is the square root of NPQ, so square root of 335 times 0.94 times 0.06 will give me 4.3467. Since we're using a normal model, we're going to use Z. Z is equal to 321. The reason I'm going to use 321 is that'll be the number that I'll have to bump someone. So 321 minus 314.9 divided by 4.3467 is equal to 1.40336. So we're going to draw our normal model. We're going to draw our line at 1.40336 and shade to the right. Finding that probability will give me 0.0803. So I have a 8.03% probability the airline will have not enough seats and will have to bump someone. A basketball player usually makes 57% of his free throws. Tonight he made 9 shots in a row. Is this evidence that he is on a winning streak? That is this streak so unusual that it means the probability he makes a shot must have changed? Explain. Again, we're going to find our mean and standard deviation. So our number of trials is 9. Probability of success is 0.57, so the mean is 5.13. Our standard deviation is the square root of 9 times 0.57 times 0.43, which is 1.485. Using Z, we're going to have 9 minus 5.13 divided by 1.485. The reason I'm using 9 is that he made 9 shots in a row, so that was 100%. Z equals 2.60566. Drawing our normal model, shading at 2.6 and everything to the right, we get 0.005. So the answer is yes. If his success rate were still 57%, he would only have a 0.05 chance of making 9 shots in a row. That's an unusual result. So what can go wrong? Be sure you have Bernoulli trials. You need 2 outcomes per trial, a constant probability of success, and independence. Remember that the 10% condition provides a reasonable substitute for independence. Don't confuse geometric and binomial models. And don't use the normal approximation with a small n. You need at least 10 successes and 10 failures to use the normal approximation. So what we've learned is Bernoulli trials show up in a lot of places. Depending on the random variable of interest, you might be dealing with a geometric model, binomial model, or a normal model. A geometric model is where we're interested in the number of Bernoulli trials until the next success. A binomial is where we're interested in the number of successes in a certain number of Bernoulli trials. And a normal model is to approximate a binomial model when we expect at least 10 successes and 10 failures.